Our guest today is Professor of Economics at Baylor University, whose research interests include mental health care, sex work, and drug policy. In 2021, he published his book, Causal Inference, the Mixtape, which looks like this, and since then has written extensively about causal inference in his book, Causal Inference, the Remix. He also runs online workshops lasting 3 to 4 days, where he dives deeper into specific issues regarding causal inference, and also trains people in coding as well. So without further ado, it's my pleasure to welcome Professor Scott Cunningham. I hope you're okay. And
Thank you, Anna.
we're ready to answer some questions. Okay. So I mentioned the words causal inference in that introduction about half a dozen times. So just to make sure we're all on the same page, because it's going to be our main topic today, can you just explain what exactly we mean by causal inference?
Yes. So causal inference is a field within another field called econometrics, and it is an applied statistics area that's meant to try to figure out whether something that a person does, or something that a country does, or a state does, or a city does, in terms of passing a law or something like that, tries to figure out what effect it had. And the history of causal inference it goes back to the discovery of the randomized experiments in the early 20s, but that was sort of a key part, a key point, because when we discovered what randomization did, we were able to kind of make a lot of progress on causal questions, but then there were lots of situations where you couldn't run randomized experiments, and that's where other developments in causal inference kind of came about, which were these non-experimental approaches to the same kinds of questions.
Great. Okay, so thank you for that, and hopefully that everyone watching will have some familiarity with econometrics at least here, but so they might sort of be somewhat familiar with these topics already, but can you just talk about some of the problems that come up when we're trying to do causal inference?
Yeah, sure. So let's say that so aliens come to planet Earth, and they watch the COVID epidemic, and they know something bad is going on. And they take these measurements from outer space, and they say, well, the people that are in the hospitals that have COVID are dying, and at really high rates, and the people that are not in the hospitals that have COVID are not dying nearly as much. And they conclude that the hospitals are killing people, right? And so so why did they do that? Well, they compared a treatment group to a control group. They've got a group of people that are being treated with hospitals that are similar, with respect to having COVID. And then they compared them to a control group, a group of people that didn't. And, and they come to this conclusion, which is that, well, since the treatment, hospitals, is correlated with mortality, it must be that hospitals are killing people. And it's real easy to kind of see that the flaw, in their reasoning. And it's because, that the reason these people with COVID are in the hospital is they're already much, much sicker than the ones not in the hospital. So that's an interesting problem, because obviously, it's extremely important to figure out if hospitals are killing people, or if anything is having the kind of harm that you observe if you just look at correlations between things, or things kind of occurring together. But if you don't have a framework to be able to say, well, what will I do to be able to set up a to set up the problem so that I can know whether hospitals are killing people or not. Then, and all you can go upon is correlations. You'll make the same fatal error as the aliens, because at some point you're going to be working on something that you don't know. You don't have as much information about the reasons that people are in the treatment. And so causal inference is essentially a formalization of a way of thinking, and a mathematical formalization of it that can give us some confidence that what we are observing when we're comparing two groups is probably not that kind of selection bias that the aliens were making errors about. It might be more likely causal, but it requires a larger framework of thinking about causality, and it requires some particular sets of tools.
And you go into those tools in the book, which I've read, and there are several things that kind of struck me about. So even when we have, say, the potential outcomes model, and these assumptions associated with that, there are still problems. With, for example, sorry, what was it? It was concentrated leverage, and there was a paper by Young in 2019, which addressed the fact that it kind of has very serious consequences for academic research. Could you explain that a bit to our audience?
So if I remember correctly, that's the one with the outliers. And
yes,
so still when you're doing your analysis, let's see. So let me just remind myself that paper he's looking at.
I've got a bookmark. I'll find it for you.
149.
Yeah.
So this is where he does the randomization inference.
Mm-hmm.
Yeah. Okay. So right. So I think that what you're doing in this, well, one of the things he's doing in that is he's trying to look at, so that's an area called randomization inference. And with randomization inference, the goal of randomization inference is essentially to try to figure out the likelihood that the number that you get in any comparison between two groups could have come from chance. It doesn't tell you it's causal, but it can at least tell you, the likelihood that it's whether or not it is or is not consistent with like essentially just a piece of fake noise. Okay. And sometimes when you use traditional statistical inference methods, they're very sensitive to outliers. And so there's things that you can do that are a little bit less sensitive to those outliers, and trying to work with ways of addressing, that can be done through transformations of the data, and it can also do with trying to sort of find units that are unusually influential in whatever statistic that you're measuring, and just removing them. Because if it's like extremely sensitive to just one highly large valued observation, many people find that not very satisfying, in terms that they feel like they maybe don't want to they maybe want to find more, they want to believe a number that might not be just being skewed by some unusual distribution.
Mm-hmm. Yeah, so I think the results of that paper, where it says here 35% of 0.01 significant reported results, so that's the p-value 0.01, were found to be insignificant at that level. But on the other end of that, lots of people here will have used the p-value of 0.05 quite frequently, but there is a sense that these significance levels are actually quite arbitrary. So what do we do with that, and what does, you know, the sort of arbitrariness of the p-value itself have on the quality of academic results?
Yeah, people have really strong opinions about the where we make the where we actually create certain cutoffs. I guess I don't have strong opinions about, you know, that where that needs to be. I'm not sure that, I mean, having statistical inference is a way of speaking about confidence that we have about our null hypothesis. So whether it's at 0.05 or a different number, I guess I'm not probably the right person to have a strong opinion about that. So yeah, I don't really have an opinion about the use of the p-value per se.
Okay, that's perfectly fine. Okay, well, we have the book open now anyway. So I just wanted to ask you, you know, there's quite a lot of like econometrics on the market, and also very popular books such as Angus and Fishker. So what did you want to contribute when you were releasing this book, and what did you want your reader to get out of it that they wouldn't from other textbooks?
Well, Angus and Fishker's is the best book in the market for sure. I mean, theirs is the classic. You know, Josh Angus won the Nobel Prize like 4 months ago. You know, I think that the real value of having more than one book is just simply that sometimes certain people find certain things more accessible with some writing than others. And so I think that the things that are different about my book, they're not better, they're different, is mine is written more recently. So there's a lot of material that I go into that Angus doesn't go into. His doesn't cover randomization inference. His doesn't cover directed acyclic graph models. And he doesn't cover synthetic control. He doesn't mention some of the weaknesses of canonical approaches to difference and differences like I do. And his doesn't include code. So, you know, part of what is what was new at the time, it's now quickly, the market's kind of filling up with lots of people trying to write on this topic that are introducing free books. Mine was free also, free books with code. There's lots more of that now too. Nick Huntington Klein has a book. Others have books. So that's one thing, is there's some content differences, but I think that my style of writing, what I'm told, is seems to get across to some people that maybe had a harder time with Mostly Harmless. I'm not sure what exactly that is. I think that you know, what's different between me and Josh Angus is, you know, he's a Nobel Prize winner, and I'm just a normal person. And so I tend to think, well, if I can explain, when I'm writing the book, I was always thinking, well, what about the person in the room that was like me, that, you know, was always really confused in econometrics. And you know, my background was not economics or math. I was an undergraduate major in literature, and so I don't really have a traditional economist training background. I mean, I have a traditional training, but not a story of that. And so in my coursework, I was always really just dying to do research and loved economics, but didn't feel like the smartest person in the room. And so I write to myself. When I write, I'm always thinking, well, what can I do to help make this clearer? How can I get this across? And that usually is not with math for me. It's not usually with math. It's sometimes with code. It's oftentimes with pictures, practical advice, telling stories, things like that.
Yeah, and I think that really comes across as like, because your sort of guidance to how to do good research isn't just, the models themselves and the estimators. There's a great deal of practicality, not just in coding, but, one of the phrases I kept coming across is shoe leather, which I found quite interesting. You seem to have a real appreciation for the sort of like the hard work, outside of the, state lab, for
Right.
doing a good research project.
Yeah.
So I don't, some of our audience might be embarking now on their undergraduate theses. So I don't know if, you have any advice of them that you want to share, apart from buy the book, maybe.
On doing research?
Yeah, I'm doing research.
Yeah. So, well, I think that so the thing, it's funny, like, so if you're embarking on your undergraduate projects to do research, I think you want to think about being successful at doing it. I think that's your goal, is to be successful, and to be successful has a couple of different meanings to it. One is to do it, to actually be able to turn it in on the date that it's due, and that actually eliminates a lot of projects. There's a lot of things that you won't be able to do. So that's one. Secondly, I think the thing to remember and to give yourself permission on is to remember that this is the beginning of your career. This is the beginning of your research career, and so you wouldn't ask of yourself in a recital, like a piano recital of your, when you're just beginning to learn the piano, you wouldn't ask yourself of that the same things that you would ask of yourself in 10 years or in 20 years. And so the goal, I think, is to have a question that you care about, that you find interesting enough that you would say, I want to work on this. I care about it, and you get to decide why it's important or interesting. That's one. You're going to need to partner with someone that, basically at minimum is not going to be hostile to your progress, but at best, brings out the best in the project, brings out the best in you. And so lots of times that selection of that advisor on the project is really important, finding somebody that you really think you can learn from, and working on projects that what are your goals on the project? Like, I think if your goal is to learn how to use synthetic control, that's perfectly fine. I think that's a perfectly legitimate reason to work on a project. If your project is you want to learn more about, the relationship between minimum wages and employment, that's also perfectly fine. I think, like, giving yourself permission to have lots of different reasons why you find a project interesting is something that you should feel okay about. And then the nuts and bolts. So if it's going to be a causal, kinds of project, there's a couple of ingredients to it. And probably at the undergraduate level, starting out, these are the things you want to think about. Probably using my book. I don't mean using my book, but like the chapters for my book is a good kind of thing, because the chapters kind of summarize pretty much the normal designs, and I think thinking about your project and saying, okay, if I'm gonna do this using instrumental variables, well, then this is what an instrument should look like. And that's going to shape, not just what the question is, but it's going to shape what data sets you're getting, and the approach you're going to take. So probably the most important thing is to try to get the data set as soon as possible. You know, the sooner that you can get the data set, the sooner that you can come up with a tractable question, the better. And that probably will involve, should involve talking to your advisor, relatively frequently early on to kind of get that nailed down.
Mm-hmm. Okay, that's interesting. And I think something I came across, which is a tool I've used before, which I hadn't really thought much about, was the DAG, or the direct acyclic graph. And that, I'd never really considered how powerful a tool that could be for like constructing, inference models. So could you talk a bit about like, what the unique benefits of those are?
Yeah. So first of all, the directed acyclic graphs are really great, because even though they're inside the graphs is all these, this mathematical modeling, it just displays it with arrows, and the displaying of it, the notation for DAGs is actually just, drawings. And I think that for a lot of people, like there's a certain group of people that think in terms of equations, and there's a certain group of people that think visually. And I think, oftentimes those people that think visually have kind of felt a little boxed out of these, even though they're of the same level of ability. And so I like that DAGs kind of provide that visual framework for thinking about causality. The second thing about DAGs is they really reward your knowledge and your expertise in an area. And so, what you're doing in a DAG is you're writing down exactly what you believe about the world, what you believe about the phenomenon that you're studying. So if you say, well, the reason people go to college is because they have higher incomes, and the reason they have higher incomes is because their parents went to college, and the reason their parents went to college is because they didn't face discrimination, and the reason they went to college is because they didn't face discrimination, at least a little bit. And you can start telling this story, but the story gets really complicated, and it's hard to hold it in your head. And the DAGs provide like an accounting of the story to print it down and to start thinking exactly about how variables connect to each other in your mind causally. Well, once you kind of commit to that story, and you say, yeah, I think this is what's going on. I think this is basically what's going on. I mean, I'm not capturing the whole thing, but as a simplified model, I think that this is a reasonable explanation of going to college and its effect on earnings in England in 2022. Okay. Well, once you sort of say that, now you can see exactly the things that could lead to those flawed reasonings that the aliens had when they were looking at the hospital mortality. You can see exactly formally where the selection bias is coming from, where the omitted variables are. And if you can see them, then you can see what solutions may or may not be possible in the data set that you download. And so what DAGs do is they point to solutions, and they point to what a solution would look like. Not that you have it, but it'll point to what a solution will look like. And it'll make it very explicit that in order for this model that you chose to have any chance of recovering a causal effect, these three things must be true, and oftentimes that's not available. It's there. It is always there. It's not that it's not available. It's always there in any kind of econometric approach. It's just that it's lots of times very obscured. It's very obscured by the actual statistical notation.
Yeah, and so you kind of talk about how DAGs come from Judea Pearl, who is still a computer scientist, and I kind of appreciated like having a brief history of every estimator as well, seeing where they kind of came from, the crossovers with, say, epidemiology and computer science again, and it kind of gave the impression that causal inference is very dynamic, it's a constantly evolving field, which you might not get from, an undergraduate econometrics
Right.
lecture.
Right.
And I think this is most of all the case in difference estimation,
Right.
which has recently had like an explosion in the literature. And I think it was one of the first estimators that I came across at Bristol. Maybe that's changed, and I'm getting quite old now. So just in case, the audience doesn't know what a difference is, because this is like the thing I really want to talk about. Could you just like give a brief?
It's interesting that since we're on everyone's in England, it was invented in 1854 by John Snow because of the cholera epidemics that kept hitting London at the time throughout the world, I guess, but it's usually associated with England. The dominant theory of diseases like cholera, I'm not sure if it was all diseases, but it was definitely for cholera and other diseases, was that you were dying because of really smelly air in the city, pockets of vapor that were foul. And so and it was because the industrialized London, early on industrial revolution London, was just it was at the those early industrialization periods, there's just production of a lot of sewage, there's not a sophisticated infrastructure of sewage and filtering, and piping and things of that nature. So there would be just like open areas of cesspools and things like that, and waste. And so it's kind of like maybe not even all that. I wonder if it's all that surprising really that people would think that, because if you can't see a microorganism, then you're just left to come up with good theories. And that one seems like that's probably a good working theory for a lot of things that are being transmitted through sanitation problems, because that was their solution, was sanitation solutions. And so so Snow had over decades, because he had worked frontline treating patients with cholera. He had tried all of the treatments that people were considering for treating cholera under this it was called miasma, under this miasma hypothesis of disease transmission, and they didn't work. At least he didn't think they worked. I mean, that's the kind of thing, is like you don't really know with causality if it's working or not. So because you only know in large aggregates, you don't really know at an individual level if it worked or not. But he became convinced it didn't, and he had all this anecdotal evidence, and nobody believed him. Because it would be it's kind of like, to really understand the opposition that Snow faced, it would be like in COVID, okay, telling people that vaccines don't work, right? That was the context for John Snow. It was extremely, he was a miasma denier, and so he did not have a good reputation, as the sense I have of this, and people did not take him seriously. And so he was always fighting this uphill battle. And that kind of anecdotal evidence that he presented just was not accepted. So we had these two pieces of evidence. We had these three. So we had this book, 1854 book. And the book is brilliant for lots of reasons. It's brilliant. One is it's just brilliant for the rhetoric of a scientific argument, of just kind of this layering of evidence, this kind of the way he moves through personal anecdote, description. He kind of makes arguments where he's sort of trying to argue through deduction and saying, well, if miasmus was true, we would see deaths here. We don't. If it wasn't true, we would see it over here, and we do. And so he was kind of like arguing through these kinds of a particular style of rhetoric. And then he presents two pieces of evidence. One is actually this right here. I don't know if you can see me. This is the Broad Street pump map. He actually by hand makes this map of the Broad Street. I think it was called something else at the time, but yeah, I know it's Broad Street. So there's a pump right here, and it's this neighborhood, and I forget the neighborhood, but I've been to it. It's a pub now, and he says, he takes this map, and it's probably hand drawn or something. I mean, and then he gets deaths, individual level deaths of cholera mortality, and lays it on top of the map. And like with these little bitty blocks, and everywhere that you're seeing all these black dots, it's either a pump, a water pump, an open water pump, or it's deaths. And so like right there is a water pump on Broad Street. And all around Broad Street are deaths, except for here at the brewery. And there's no deaths at the brewery, but all around there's deaths. Well, at the brewery, they don't get their water from the Broad Street pump, and they have like their own well. And then, but the Broad Street pump is apparently contaminated. So he's kind of like arguing almost kind of anecdotally still. It's a famous map because in the history of data visualization, it's one of the most important maps that's ever been created for displaying quantitative information. But which is a big part of causal inference. It's a big part, showing pictures. I try to emphasize that a lot in the book. But then the second thing that happens is he discovers a natural experiment. And this kind of gets to this point I made at the beginning, which is we've known about how to identify causal effects going back to 1925 with Ronald Fisher. Ronald Fisher is the one that's credited with saying that if you physically randomize a treatment, then you can just compare the treatment group and control group, and that'll tell you whether or not the treatment caused anything. See, that was the problem. The aliens were not physically randomizing hospitals. They were just looking at naturally occurring separation of people into and out, selecting into and out of hospitals. So, well, you can't randomly assign, usually you can't there's a lot of things you can't randomly assign, right? Like you can't randomly assign, he's not going to be able to well, first of all, this is 70 years before Ronald Fisher, so he didn't even know about randomization. But putting that aside, oftentimes an individual researcher is not in the ability to go to a city and say, randomly assign all the drinking water, some of which will be contaminated with feces and some of it won't be, right? You're not going to be able to get that past institutional review boards very easily, even though it's obviously of a critically important question. I mean, it's like absolutely massively important. You're oftentimes not physically able to do it, or financially or whatever, especially for undergrads, especially for me, a grad student, a professor. So what did he do instead? He paid attention. He believed that cholera was coming through the Thames River. That's what he thought. He thought it's coming through the Thames. He had a whole theory. He said, what's going on? He'd never even seen a microorganism, right? There were no good microscopes. And he's saying, no, this is what's going on. They're getting sick. They're eating and drinking things that have cholera in it, microorganisms. He'd never seen one, but he articulates it's a living organism in the food and the water. It's going into the stomach. It's causing poison. It's causing the poison to expel water through waste and killing the host, but going into the river. And then it's repeating because our pipes are in the river. And so the pipes are feeding into these neighborhoods. So he starts reading into industry magazines on the utility companies, boring literature, right? But this is the kind of stuff you and I could do by setting up Google alerts on the stuff that we're interested in. Just start learning about things out there and reading the newspaper and reading books and magazines about the stuff you're interested in. That's where all the good ideas come from. They don't come from econometrics. They don't come from my book, right? And so the econometrics in the book is more about what you do when you found it, when you found the idea, not getting the idea. And so he learns of an experiment. London passed a law that said all the utility companies had to move their inlet pipes upstream above London. Okay. And not because of cholera, but because, again, they were just focused on sanitation. Well, everybody cooperated except for Suffolk and Vauxhall, which was this utility company that serviced this large neighborhood that was also serviced by a company called Lambeth. And so he said, I have a natural experiment. He didn't call it that. This was also so innovative about Jon Snow. Jon Snow is truly a superhero, you know, like in terms of like scientist. He's a scientist. That's what he is. He is our scientist, because he teaches us how to do good research, pay attention, meticulous data collection, be obsessed with data quality, getting all the facts right, talk to people. And so he learns this experiment, which was he's going to do a before and after comparison of Lambeth. He's going to do before and after comparison of cholera mortality of Suffolk and Vauxhall in these neighborhoods. And then he's just going to compare those before and afters. He didn't know that was called difference in differences. He didn't know the conditions under which that would actually be valid. And the thing that you're talking about now is the recent renaissance in diff and diff is about, you know, there were situations where that we were doing what we thought Jon Snow was doing. There were situations that we were trying to do that, you know, it wasn't doing what we thought it was doing.
No, and those, sorry, carry on.
Go ahead.
And I think what you're talking about, you know, people started introducing differential timing for when these
the differential timing.
Exactly, yeah. And that's where the problem started arising. So, you know, not to get too advanced too quickly, but could you sort of like, so there's an econometricist called Andrew Goodman Bacon, and he decomposed the difference in difference estimator with differential timing, and that was quite revealing about what people were actually doing when they were doing this differential timing. So could you explain that?
So it's actually kind of funny. I mean, just for everybody on the call to know, it was actually a guy at University College London named Coral Borisok and Yarvel. They were both graduate students. Basically what happened was there was simultaneously Harvard, MIT, Vanderbilt, Andrew Goodman Bacon, kind of these like simultaneous discoveries that the canonical econometric estimator called it's a version of ordinary least squared. It's called two-way fixed effects, or that's like what its jargon is called now, two-way fixed effects. It used to just be called panel fixed effects, but now it's called two-way fixed effects. Well, that's the thing everybody used in a particular situation where a city might get, different cities might get minimum wages at different times. And it's really trivial to estimate that model with OLS, like, because you learn in your econometrics classes, you can do what's called multivariate regressions. You can put in more covariates and you can estimate the parameters on those covariates. Well, why can't we do that with difference in differences? That's all, you know, difference in differences is a variable, right? It's a variable taking on a value of 0 or 1 for different units at different periods in time. Why can't we do it? And so people did it, you know? And so well, it turns out that you can do it. And when, you know, units get laws at different points in time, you can estimate that. And you can estimate the causal effect on those laws if you're willing to make a lot of assumptions. And those assumptions were kind of buried in the statistics that we learn in econometrics classes, that the note, and again, it's kind of like, it's not the weakness of the notation. It's more of like the lack of completely spelling out exactly what that assumption meant. And so there's an assumption called strict exogeneity that said, you know, the error, it was all about the error term. You know, it's like, so like undergraduates, if you find that, you know, all this stuff you're learning about the error term, right? Like you think you're supposed to like understand what an error term is. You're not alone in finding that a little bit mysterious, because even PhD economists didn't fully understand what exactly was implied by this strict exogeneity assumption, which essentially was that everybody's treatment effect was exactly the same. So like if it was Not only that, it was the treatment effect was the same and never changed over time. It was not dynamic. So that meant, like imagine cities get a minimum wage and it has some effect, whatever it is, has some effect on employment, but the effect on employment gets bigger and bigger over time, right? Well, economic theory has that kind of stuff all the time. Elasticities change over time, right? So, you kind of expect certain things to be one way on the first day to be different on the 10th day, and different on the, the year, as like the inputs become more variable. Well, that is a problem. That actually turns out to be a problem for difference and differences, because that two-way fixed effects says, well, I'm only going to be able to do what you're asking me to do if that does not happen, if it does not change over time. Well, so Kirill, Borsak, and Yarvil have this working paper where they were identifying for the first time explicitly it was flawed. Simultaneous to that was a team at MIT, Sarah Sun and Abraham. So Sarah Abraham and Sophie Sun, they do it in a different way. But I think it is true that Andrew Goodman Bacon, his paper really struck the nerve. That does. You can see that reflected in the fact that the citations for Andrew's paper are about 2.5 times everybody else. And so, that, and I think part of it, it's kind of fun. It's going to sound kind of silly, but I really think this is true. Andrew was very active on Twitter. And at the time, Kirill, Borsak, Sophie Sun is not on Twitter. Sarah Sun and Abraham. Sarah Abraham is not on Twitter. And at the time, I don't think Kirill was either. And I don't think Yarvil was either. And so, and then the second thing was it's written in a by non-econometricians, and I think sometimes Andrew is an applied microeconomist. He is a very good writer, and his communication of the ideas, it's not heavy on a lot of proofs, which is what econometrics, there's a technical bar to econometrics, and the technical bar is intensive proofs, right? And so the works can get very technical, and it can almost be like, all the more reason why applied people don't read these econometrics papers. And so Andrew's paper showed the flaw and showed why it was happening and made it so easy to understand. And it all really, it sounds kind of ridiculous. I don't think people have actually talked about this, and it's embarrassed. I kind of embarrassed to offer it as a suggestion because I think people would laugh, but I actually think it's true. I actually think Twitter drove that. Twitter drove that revolution, because it was non-stop on Twitter for about a year through constant threads of total freakouts on Twitter of people just, and proving it over and over through simulations and workshops and all this stuff. They were like, and you just see these waves and these waves. Nobody really remembers it. I would love to go back and see it, but like I was there and I was doing a lot of it too myself. And people were just like nauseous because all of us had different papers that we were like trying to publish, or had written different papers and we're now embarrassed, and we're wondering like, oh gosh, if everything is my entire career garbage, it's like it's like you're just worried. Because different is the single most popular design in all causal inference.
Yeah. And you mentioned that it's really struck a nerve, and there are lots of attempts to sort of address these problems. And if the audience is interested in some of this research, then go ahead and try and compute it. You never will, but I'm sort of aware of time at the moment, so I'm going to leave it at that for now and hand over to the audience question and answer session. I did want to ask you about Card, Angrist, and Invens, and Cooper as well. But maybe if the audience is interested in that, then there's now an opportunity to ask about that. So,
sure.
Gus, I don't know if you want to take over at this stage or not. Okay, he's coming.
Sorry, can you hear me? Wait,
yes, you can, yeah.
Anyone have any questions? None coming in so far. I guess if you want to quickly ask your one, then we'll wrap up, because I think that Professor Cunningham might have to go at some point, he mentioned, but I'm not too sure.
Yeah,
I
that's
have
fine.
a little time. I'm okay. Yeah, I have to run to class in a little bit, but I'm okay right now.
Okay, that's fine. Okay, I'll just ask my last question, and apologies for this sort of starting late and now running a bit over. But so if you just, obviously this year's Nobel Prize or last year's Nobel Prize was it was basically to causal inference in a sense, and the names I mentioned are all like titans in this field. So can you tell us about what makes them so outstanding and what their contributions were?
Yeah. I mean, it's David Card, Josh Angrist, Hito Embens, and it's you can tell a whole story about these three men. In many ways, they're kind of like representatives of a larger group. Probably they're David Card and Josh Angrist long-term co-author Alan Kruger. He passed away about 3 years ago. If Alan Kruger hadn't passed away, you could have easily imagined it'd go to David Card, Alan Kruger, and Josh Angrist, and probably been more of a labor prize. And then Hito Embens would have won it with a guy named Don Rubin. Because so it's like this kind of decision to give the Nobel Prize is always this like constrained optimization problem, because you can only give it to 3 people and they all have to be living. So there's like a regression discontinuity a little bit with that, because Don Rubin and Orley Ashenfelter could have just as easily won it also. So David Card's been called the greatest labor economist of his generation. He's sort of responsible for the shift towards this kind of empirical work that we all kind of take for granted, of the way that we evaluate laws with treatment groups and control groups, using randomization and non-randomization. And he's just produced a huge number of classic works that have just completely changed our understanding of how labor markets function, from the minimum wage to education to immigration. Okay. Connected to that, he was actually Josh Angrist's professor and his advisor at Princeton. All of that. One way to think about that prize is not only was it for causal inference, it was for Princeton. It was for Princeton University, 1980s Industrial Labor Relations Department. Orley Ashenfelter, David Card, Alan Kruger, Josh Angrist, and a whole bunch of other people. And they're the ones that began to shift empirical work away from kind of a densely theoretically model-based approach to this idea that we just need to be focusing on physical treatment assignments in the world. And if we can find random physical treatment assignments, that's best. And if we can only find these non-random natural experiments, that's second best. And that kind of unleashed everything, because when it started to move causal inference away from the dense neoclassical micro models, all kinds of stuff happened. Not only was the focus on the natural experiment, which everybody knows about, but it also led to different kinds of questions that were able to be studied that didn't have a model. My research on sex work, for instance, and violence, that's impossible to do without design-based causal inference, because there is no model of that. You could make one and you'd just been making something up, So all kinds of questions get opened up that just really that were like more speculative. Josh Angrist, and Hito Embens do all this pioneering work in the mid 90s on a technique called instrumental variables, and basically show exactly what instrumental variables is estimating, and sort of like, kind of like Andrew Goodman Bacon, they do this decomposition and they show exactly what the two-stage least squares and all these IV estimators are estimating, which is both good news and bad news. Good news is it actually is possible to estimate these treatment effects, which at the time was not known. And when you have like non-compliance, and then, but then secondly, you could not get the full treatment effect. You could only get it for a particular group of people, and called the complier population. So it was really, really powerful, really powerful breakthrough. And, you know, it was kind of justly recognized as really, really important.
Brilliant. Okay. So I think that might be all we have time for. And I know people want to have their pizza and their wine and whatever else they want. And I don't want to keep you too long, Scott. So, yeah, thank you. That was a really interesting talk. And I know I learned a lot, and I hope our audience did too. And sorry, it's all been a bit awkward and a bit messy today. But it was a pleasure to speak to you. And
nice to meet you too.
You know,
Bye, Gus. Bye, everybody.
Bye.